So we move on. We'll have time for questions at a later point, just before lunch. So we'll wait for those, and I'd like you to be thinking through a few questions to ask our two experts this morning. Our next speaker is Dr. William Oxenham. He is the Abel C. Lineberger Professor of Yarn Manufacture and Associate Dean of the College of Textiles at North Carolina State University. I should say also that he's an export from Britain because his appointment in 1992 followed 20 years of teaching and research at the University of Leeds, where he gained both his BSc and his PhD degrees. His research interests cover all aspects of yarn manufacture, and he's presently involved in projects dealing with yarn abrasiveness, vortex and compact spinning, thermal stability of processing aids, interaction of fibres and high-speed airstreams, the significance of fibre crimp, micro-machines in textiles, electro-textiles, information engineering, niche markets for textiles and decision models for plant location. And he still had time to come and see us here today. So I ask you to welcome Dr. William Oxenham. I ask whoever's phone is ringing please to switch it off or to take the call outside the auditorium. Thank you. And I welcome Dr. Oxenham. Thank you.
Good morning, and thank you for that wonderful introduction. I think I wrote it myself. It's a pleasure to be here, and unlike most of the other speakers in the plenary sessions, I'm a simple technologist. I'm a spinner. I don't know anything about management. All I know is about the technology of yarn production. So it is a different perspective you're going to get. What I'm going to talk about is fairly focused. I'm going to concentrate on developments in short staple spinning, particularly emphasizing what's happening in the cotton area. The picture here in the background, just in case you don't know, is the College of Textiles at NC State. So 1, 2, 3, 4 buildings, that's the actual college. Library top floor, faculty offices, lecture rooms. On the basement level we have all of the manufacturing for spinning, weaving, knitting, and then in the real basement over here where it should be is the dyeing and finishing to keep them below ground. This, by the way, is to point at people whose telephones go off. So. I'm going to concentrate exclusively on the spinning machines. But before you can get a spinning machine to work, you've got to have the right fibers. My friend and colleague, Dr. Yahya El-Maghazi, is an expert in this area, and I think I get 10% commission for saying he's got a wonderful textbook which explains the impact of fiber properties on spinning and yarn quality. If we look at modern spinning methods, it's more and more important that the fibers that are fed into the spinning machines are clean, net-free. There's a uniformity of fiber length, but also uniformity of all other properties. Fineness, color, wax content, all of these will produce variations in the ultimate yarn, fabric, and garment if we don't look at them to start off with. So preliminary processing fiber selection is absolutely critical for the successful development of any spinning system. In terms of what's available, I've grouped it the way I think it should be, and that is the two bottom ones in red are systems which work readily for cotton. In other words, ring spinning, roller spinning work well for cotton. Composite spinning, friction spinning, niche market, very small area penetration. Jet spinning, it's predominantly polyester-rich blend, so it's polyester with some cotton, but it's got to be polyester. It's not 100% cotton. Vortex spinning, slightly different color. It's more cotton than polyester, so we're talking for jet, polyester cotton, for vortex, cotton polyester. And then finally, the new one at the top is centrifugal spinning, which is a potential system of spinning which will work for cotton if it becomes commercial. Throughout the conference, I've heard lots and lots of comments about yarn quality, and I really do believe that it's something we talk about, but nobody understands. Because, you know, and the top line sums it up. Quality cannot be measured. There is no way of measuring what quality is. It's lots of things. It's a bit of strength, it's a bit of elongation, it's some hairiness, but then we've got to take it further through and say, right, how does the fabric dye? What is the garment drape like? And all of those aspects must be considered. It is not, as unfortunately one speaker said this morning, meeting standards. We can meet standards on things like regularity and meet standards on things like strength. The yarn can still be unacceptable in terms of customer preference. So it's careful to balance all of these different things. And this is my favorite slide. I showed it every lecture I give, and all my students have it ingrained, carved on their brains. It is this one. If we look at yarn quality, there are lots of inputs and there are lots of outputs. In terms of inputs, it's fibre selection. In terms of spinning system, in terms of cost. I can spin the best yarn in the world. You know, I use 3 roving frames and I go back to a mule, and I will spin it really slowly and it'll be almost perfect, but totally uneconomic. On the output side, we've got performance and processing, things like strength, regularity, abrasion, aesthetics. We used to call this tactivisual. It's to do with touch, it's to do with sight, it's to do with what it looks like, what it feels like. But this is the real hard one, because everybody has their own preferences, and when we're trying to design yarns and fabrics to meet some quality aspect, it varies. It varies from nation to nation, from country to country, from north to south, from east to west. And the other one again is cost. You know, it may be slightly weaker yarn, but if it's 10 cents a pound cheaper, it may be good quality. I change my perception of quality depending on each of these aspects. And I want to keep that in mind as we go through the presentation, because whether a spinning system succeeds or fails depends on all of these attributes. Not simply because we can spin faster, not because it's stronger. It's got to take everything into consideration. If we look step by step at each system, ring spinning, first of all, it's the standard by which all other spinning systems are judged. And what happened in ring spinning, there are a whole group of things in this area here. And there was sort of a symbiosis. They all came together and fitted together. Which came first doesn't matter. But it was availability. There were available automation. Automatic doffing was available, splicing was available, winders were available. It was putting all of those together, so we said, look, if we've got longer machines, automation becomes less expensive per spindle, and therefore we can apply all of these. So we say bigger machines mean automatic doffing, link winding, automatic winding, and defect removal and splicing at the winding frame. If we do that, package size becomes less critical, so we go to smaller spindles, smaller ring sizes, higher speeds, and therefore what happens overall is we get a potential increase in speed from 15,000 to 25,000. Now these speeds are mechanical speeds. I'm not saying you take your cotton and you're going to spin at 25,000, but I'm saying potentially that's what's available simply by incorporating all these slight modifications. Where's ring spinning going? Machine's getting longer. You know, almost 1,500 spindles on a machine is potentially available today. Higher drafts is something I'll mention. The impact isn't in terms of what happens on the ring spinning machine, it's in terms of the whole of the ring spinning process. Whether we use roving feed or lightweight sliver feed. Higher traveler speed or alternatives. Compact spinning, and perhaps one of the most exciting ones, again in terms of when we're looking at quality, is this one, spindle identification. We've got sophisticated winders which will actually wind the yarn and pick out faults. It will tell us how many faults are in the yarn, it will remove faults. One of the major problems, I know when I was at Leeds for 20 years, 90% of industry problems were associated with stripiness in fabrics. Where is the source of this yarn defect? And what we used to do was we'd get a team of experts who'd go in and stand for hour by hour watching spindles on ring frames saying which one is the faulty one. With this it's possible now from information on the winder to go back and say, right, spindle 37 on spinning frame number 2 is giving us the faulty yarns. Go and change the aprons. It's that easy if we apply that sort of technology. Otimas, the Japanese machinery show, about 5 years ago, you wander around, you look at machines, you think, that's a green machine, that's a blue machine, that's a red machine. They all look the same. This one looked slightly different. It looks like a normal ring spinning machine until you get really close to it. And you find some strange things. And it's sort of going back 20 years, the reinvention. It had rotating rings where the ring rotated to minimize the amount of traveler wear and therefore potentially operate at high speeds. It had individual spindle drives, electric motor per spindle, all tried 20 years ago, thrown out. Now, I'd like to think they were thrown out for a reason, and there was, in terms of the single spindle drives, there were good arguments for using these because the power cost was significantly lower, the machine was quiet, you had full control. The biggest problem was they were big, the motors were big, and also they were expensive. Now, that I think still applies, but what I would caution you about is many ideas are being thrown out by those in Europe and America saying they can't work, and 20 years later the Japanese reinvent them and all of a sudden we're buying them back. And so these approaches seem strange, seem illogical, but may have some merit. This one, the rotating ring, others are working. Again, my friend Dr. Al-Maghazi at Auburn is doing some work currently using a rotating ring. In this case, it's supported on a magnet rather than the older systems are supporting on air on bearings. Other approaches, it's fairly involved diagram, but this is a Russian system called the Super Traveler system. And what it involves is actually an alternative to the traveler. It involves using a disc which is here, which rotates between an inner ring and an outer ring, shown clearly here. So there's an inner ring, an outer ring, and this sort of wheel. It's like a lifesaver. Lifesaver, polo mint, one of those. So that rotates around and the yarn goes down the middle, and the idea is it wears a lot longer. The caution I would throw out is these are great ideas in a laboratory, but in a mill environment where you've got rapid change in temperature, humidity, your fluctuations in the amount of fiber and fly produced, these tend to be unreliable, and things like rotating rings had also other major problems in the past. If you go back again 20 years, a lot of major studies missed one problem, and that is even though rotating rings enable potentially higher speed because they reduce the overall tension, they do introduce tension peaks. A normal ring and traveler has one wonderful asset, that is the traveler's speed can constantly change. Fairly quickly, it's light. If you start to go to rotating ring, you've got to change the speed of the mass of the ring, and then you're under major problems that knock over from the nose of the chase as you're going up and down the package. You change the winding speed to get tension peaks, which can in fact increase end brakes rather than reduce end brakes. In terms of high drafts, this is a complicated table. The only thing I would look at is say, look, on the same machine, you can either use a normal drafting system with a draft of about 30 or a high draft system of about 90. Yarn properties as measured, thick, thin, strength, and so forth, are all the same. It doesn't make any difference. But where the difference does come in is in terms of the weight of roving fed and the weight of sliver fed to the roving frame. The advantage is in the preparation. You get great advantages in reducing the number of roving frames or the weight of the sliver which is used. Zinsser showed this machine at the last ITMA. They also showed the accompanying roving frame. This was developed by Parkdale Mills in the US. They said they wanted it. It's a heavy roving spinning machine. The problem is when you start to go to heavy rovings, the rovings get bigger, and therefore this bit, the creeling, becomes more difficult. So you've got to modify all the overhead creels to accompany this within the system. Also, the automation needs some changes. Again, the same sort of changes. Operating at drafts of about 68, 70 are possible. The alternative to roving is to use a sliver. And this is an old sliver, but the principle is still the same, so we're spinning directly from sliver as opposed to heavy roving. The debate as to which is the best approach goes on. And it's split between the two camps. You've got Zinsser as one major spinning machine company saying heavyweight roving is the best approach. Reeder and Susan, on the other hand, with sliver, saying that sliver feed is the best approach. So those two, it's still a debate. Personal preference, I would say, roving is easy to automate. Compact spinning. Lots and lots said about compact spinning, lots of interest. The idea is simply to make a yarn more compact. Lots of machine makers playing with it. The question marks are cost, and in some cases it was argued that roving stop motions would be needed. Again, that would increase the cost of the machine. The pioneers in this system were Reeder, who introduced it first of all. They call it comfort spinning. Well, they call it compact spinning first of all, but compact implies hard, and therefore they said this is not the right term to use, so they called it comfort spinning. Then ultimately this comfort. And this is the setup of the machine they first introduced, shown at ITMA 99, shown previously, and at the last American Textile Machine Show, another version of this was actually shown. And the idea is simply to take the roving as it issues from the front roller. You apply a compaction zone where you suck the fibers together, you apply tension to the ends of the fibers, which gives you a more compact yarn, as shown here. So the normal yarn has got hairs, it's bulkier, the compact yarn is much, much leaner. Advantages: it produces stronger yarns, it produces more extensible yarns, as shown here. Or the added advantage is you can reduce the twist and produce the same strength as you would with a normal yarn. It's like lots of systems. You choose what you want. You know, the claims of this system are it's less hairy, it's stronger, it's faster, it's more extensible. If you want a strong yarn, you run at normal twist levels. If you want a less hairy yarn, you run at normal twist levels. If you want to spin faster, you reduce the twist level, but you also forgo the hairiness advantage and the strength advantage. So you select which parameters you want to use. Alternative approaches offered by different machinery makers giving exactly the same sort of results. Susan Elite, and this is now obviously since the recent merger, the Reeder system, which Reeder took over Susan, offered for both short and long stable. In their case, it's a slightly different, probably a more elegant solution. They draft as normal, but then they have an additional roller here with perforations. The material as it comes out is given a slight draft as it issues from the front rollers of the normal drafting system. This is where it compacts, and the suction through the apron pulls back the trailing ends of the fibers. And again, in terms of an open system, this is what's happening in terms of the compaction zone, where the yarn would normally be bulky and can be seen to be much thinner. And again, normal spinning, deep spinning. So the structure of the yarn is different. It is tighter, much more compact. Other systems, there was one by a research institute in Germany showing a similar system to the Susan system, where we had an additional apron with perforations where we sucked through to compact the yarn, and then a horrendous system from Zinsser where it was essentially the Susan system upside down, where we sucked air upwards but we had a perforated roll at the top. And this is just ways of getting around patents, so different companies can come and say, look, we also offer these systems. we're doing research, obviously, in these sort of areas at stage. We're primarily interested in what changes in terms of the structure. Something Dr. El-Maghazi mentioned in his presentation is, if we go back, anybody that's done any classes in spinning will know that this part of the yarn formation is the most important. And we've all learned about things called fibre migration, which locks the structure together. If we eliminate the width here, we should change the migration parameters, and therefore ultimately the properties of the yarn may change. And that's where our primary research interests are. But also what's coming out is this sort of figure. You know, and all saying is, look, it's confirming what the machine makers are claiming. If we go to compact spinning as opposed to normal spinning, we get a significant reduction in hairiness. Now, we come back again to quality. You look at this and say, right, which is the quality yarn? The answer is, well, it's got to be compact spinning because we reduce the hairs and therefore it's a better yarn. One of the disadvantages is that hairy yarns tend to also pull air with them. So as the yarn goes through the traveller, it cools the traveller. If you eliminate hairs, you also eliminate that airflow through the travellers, so the traveller gets hotter. So with compact spinning, great advantage, but you've got to spin at slower speeds because the traveller gets hot. So advantage in terms of further processing, in terms of spinning, potentially a disadvantage because you're losing productivity. Roller spinning. It's a great system for cotton fibers. It works really well. You know, the one fiber that you can feed into a roller spinning machine and get yarn out is cotton. Whether you get good yarn out or bad yarn out is a different issue, but it really works as a spinning machine. The amazing thing is, if you go to the States, or I suspect any other country, and you say to weavers or knitters, what sort of yarn would you prefer to process? The answer is roller spinning. Why? It gives less problems, it gives less fly, it gives less end breaks during weaving and knitting. It processes really well. In the US at the moment, there's a big problem with machinery makers where they have real difficulty in selling new machines. They have difficulty selling new machines because the advantages afforded by switching from a 6, 8 or 10-year-old machine to a brand new machine are almost negligible. It is impossible to defray that cost. It is impossible to spend down in terms of the investment. So what's happening instead is people are upgrading. They're taking their older machines, buying new components, and essentially producing new machines. The other thing is that higher speeds are coming in, faster and faster rotor speeds. The problem is they come at a penalty, that is yarn quality changes. And the biggest detrimental aspect of rotor spun yarns is the last one. The customer, whoever that may be, prefers ring spun. And this can be a customer like Levi Strauss, or it can be a customer like me or you, somebody else who says, this feels nice, it's ring spun. In terms of advantages of upgrades, these are figures from one of the machinery makers, and they say, look, take your old machine and you put in new spinning boxes. Other modifications as well, but the major claims are significant increases in production speed. Increase in yarn strength, regularity goes down, imperfections goes down, efficiency goes up, end breaks goes down. Everything's wonderful, because what you've done is, when you look at an open-end machine, all it is a winder and a spinning box. If you replace the spinning box, you've gone to almost a new machine. And so upgrading does offer significant advantages. It brings it to the latest generation. The problem in rotor spinning is, as we go faster, yarn properties change. The way we've got around this in the past is, we say, let's start off at lower speeds, 70,000, 80,000, with a fairly large rotor, 40 millimeters. As we go faster, irregularity goes up, strength goes down. The solution, go to a smaller rotor size. So you go to a smaller rotor size from 40 millimeters to 36, and as you increase speed, again, irregularity goes up, strength goes down. And ultimately, as we go to smaller rotors, we have this sort of constant change over across the speed range. If we take the mean of these, what we find is, irrespective of what we do in terms of rotor size, higher speeds are going to give us weaker yarns, more irregular yarns, but there's also another important aspect, that is the structure of the yarn is also changing. And therefore, if we take a yarn which is spun at 90,000, a yarn which is spun at 130,000, under identical conditions in terms of twist, opening roller speed, etc., and compare those yarns, the one produced the highest speed will have more torque, it will produce spirality in knitted fabrics. So there's a difference. A messy slide. It looks to have lots of information. One of the comments we kept receiving in the US was from spinners who were saying, look, we seem to be getting less and less for our open-end yarn in comparison to ring-spun yarn. So we had a student look back over statistics, and these were simply yarn prices as published in American Textile International on a monthly basis. So this goes back to 1984. Every month we had yarn prices. And we looked at ring-spun yarn prices, we looked at roller-spun yarn prices for a tens count. And we said, let's look at the difference. Let's take the price of roller-spun yarn away from the price of ring-spun yarn and find out what the differential is. And the answer is, it is increasing. But it's not a new phenomenon. It was increasing from 1984 all the way through to the current time. So there's a disadvantage in terms of cost structure, which is becoming worse and worse for roller-spun yarn as opposed to ring-spun yarn. And these two follow the same sort of trend. The answer is, in terms of what's happening at the moment, it's just that roller-spun yarn is dropping in price more than ring-spun yarn is. A similar sort of exercise, and again, the data is all over because this is the way it falls out, is if we look at the difference in terms of counts. In other words, there's always a significant advantage in terms of price for a fine yarn as opposed to a coarse yarn. And what we've done here is compared an 18s and a 10s. And I know these are not fine yarns, but this was the easiest to get to compare both ring-spun and roller-spun. But if we look at the difference in price between 18s and a 10s for ring-spun, it's increasing. You're getting more money for the finer yarn as opposed to the coarser yarn. If you look at the roller-spun yarn, it's actually going down. So the advantage of spinning a slightly finer yarn in roller is becoming less and less and less. The advantage of spinning a ring-spun yarn is becoming more and more and more. And these are small numbers, but the trend is significant. Friction spinning. I heard a paper yesterday on friction spinning. It's something I've worked on for about 6 years. This was the promise of the future. It was going to revolutionize spinning, offered great potential, and speeds of 500, 600 meters were quoted. Problems, major problems. The major problems were consistency of yarn quality. All that means is you've got one strength today, you've got a different strength tomorrow. You check two spindles side by side, and there'd be big variations in terms of strength, regularity, hairiness. Machine settings. It was an incredibly badly designed machine. There was no way this machine could be assembled without actually taking every spinning box out, one by one, testing it. When the yarn was the sufficient strength, you would adjust the settings until it was there, then you'd install that box in the machine. So it was really badly designed. In terms of why it failed, it's summed up here. That is, if we go from 100 meters a minute to 300 meters a minute on this system, yarn strength goes down, and that's despite the fact that we've increased our friction roller speed from 2,000 to 7,000 to maintain the twist. It is fundamentally a flawed system. It just won't work. It will never work, believe me, because there are fundamental reasons Why won't we? Composite spinning. I would use the term composite spinning the way the Textile Institute used composite spinning, because it's in terms and definitions, and I wrote terms and definitions, so it's bound to be right. But in this case, it's the combination of a filament and staple fibre together. So it's things like coarse spun yarns. It's things like wrapped spun yarns. Now, it's got a market. It's got a market. I know in the States it's used for things like velvets for lazy boy. It's also used to put lycra down the middle of stretch yarns. It's also used potentially to make yarns which are conductive by putting conductive polymers or wires down the middle. It's a niche market. It is really small. There's not one system that you could say is the only system for this. It can be produced on ring framing, produced on jet spinning, produced on other systems. But it's there, but really small. And I just want to bundle that whole lot together before moving on. Murata jet spinning. A system which has gained significant usage, but significant usage in the States. A lot of those positions are actually in the US. The reason why it succeeded in the States is their preference or like for polyester cotton. This system works really well for polyester cotton. One of the problems with the system, and it's unfortunate, Murata kept showing this picture, which says, you know, this is our 100% cotton. They promised it at every machinery show, and yet they never produced a machine which would spin 100% cotton. So the promise was never fulfilled. If we look at the yarn, it's a strange yarn with sort of supposed to be ideally straight fibers and occasionally fibers around the outside called wrapper fibers. And the balance of the core and the wrapper fibers are the reason why it will or won't work with various types of fibers. However, even though it's not successful for 100% cotton, if you look at it where it is in terms of other spinning technologies, ring frame is down here about, I don't know, 25 meters per minute, open end 120 to 100, the old Murata spinning system down about 200 max. The newest high-speed Murata jet spinning system is currently doing 300 meters per minute. It's fast. And the other advantage is it's fast at fine counts. It spins the same sort of speed almost irrespective of counts. The new system, or so-called new system. Murata vortex spinning is a development of jet spinning. It's a different design, but the principle is still the same. What we have is a core of fibers wrapped with other staple fibers. The system is being promoted heavily, or was being promoted heavily, and at machinery shows there was always a group of people around the machine because the claims were it will spin 100% carded cotton at 400 meters a minute. And those sort of claims are going to get people interested. The surprising thing is, even though it was officially launched at OTMAS and then at ITMA the following year, this machine's been under development in the US mills for about 8 years. The yarns, by the time it was launched at the Paris ITMA, were already being sold in places like Kmart and Walmart in bed sheets. My drawing. I'm not saying whether it's right, but it's the best one I've seen. The disadvantage of Murata jet spinning was we couldn't get enough wrapper fibers around the outside. These red fibers are not red fibers. They're the same as the black fibers, but if I did them all black, you wouldn't see them. The edge fibers come down in normal jet spinning, and the reason for this, if you look at a drafting system, the fibers tend to come out as a ribbon. So it is two-dimensional. You've got fibers at each edge of that ribbon. In Murata vortex spinning, what they do is they deliberately, instead of creating two-dimensional fibers, which create rubber fibers, create three-dimensional fibers. So the fibers come from all sides of the yarn. Simply by doing that, you can increase the number of wrapper fibres, and this is what the diagram is trying to show. This way, fibres only at the edge, this way they come at all sides, and we get that added wrap. In terms of pattern, the way this is achieved is in here we've got a mechanical component which causes the fibres to swirl. There are also pins and needles in here, and then the jets for twisting the yarn. The essential feature of this machine, before it could ever be commercialized, it's going to be automated. And I know Murad has spent a long, long time looking at various types of automation. How to make this machine automatic piecing, automatic doffing. So that's what these components are about. And the machine, you know, like any modern spinning machine, a sliver goes in, yarn comes out, and they're blue, grey, green, or whatever colour you want. A figure from Murad, again, if I was Murad, I would never publish this figure because it limits their application of the system. Ring spinning, roller spinning, they follow the trends that spinning systems have always followed. That is, as you spin finer yarns, usually the tenacity goes down. With jet spinning, there was a major problem. That is, it would only spin fine counts. As you spun coarser counts, the yarn strength dropped off dramatically. Again, with vortex spinning, you've got the same problem. As you spin finer counts, 40s, it's almost approaching ring spun yarn strength. But as you go down to 10s, it's weaker than open end. Coarse count yarns and this system are incompatible. Murata figures, again, the pictures are theirs and therefore they're going to favour their yarn. This is the vortex yarn, a ring spun yarn, a roller spun yarn. And the vortex is claimed to look more like the ring spun yarn. Research on MVS, vortex spinning. Again, we try to concentrate on structural parameters, process parameters, what changes in terms of the structure and how this is affected by the processing parameters, how that in turn affects the yarn quality. In addition to the work we're doing at State, there's lots of work also going on in the industry. And typical results, the yarn structure is really strange. If we think back to open-end yarn always had the problem of wrapper fibers and you cut them and twisted. Vortex spinning was jet spinning was somewhat similar. You had these wrapper fibers around the outside. If you look at the structure, sometimes you had wrapper fibers, sometimes you didn't. Vortex spinning is also a complicated structure. But the intriguing thing is you find parts of it when you untwist it, it looks like a two-fold yarn. And so we take this as an original yarn. As you untwist parts, this is what you end up with. In close-up, you get this. Now, this isn't two yarns, this is one yarn. Take the yarn, untwist it, and you've got a core component which would be normally parallel, and these fibers here would be wrapped around the outside. So we've got a huge number of wrapper fibers. And another example again. This is one yarn, core, wrapper fibers. Simple research results, and again we come back to that quality word. The advantage of vortex spinning is it will spin cotton, rich blends, better than jet spinning. And if we look at the two lines, the blue line and the red line, they start the same. This is jet spinning and vortex spinning. When we're spinning 100% polyester, there's no difference. But as we increase the amount of cotton in the blend, in other words, this is 100% cotton down at this end, the strength of the jet spun yarn declines rapidly. The strength of the vortex yarn also declines, but I know we can spin about 10, 12 grams per tex for 100% cotton. So again, we jump up and down and say we can spin 400 meters a minute, fairly strong yarn. The problem is you've also got to look at the bottom. This is the extension. Elongation and break, and when you look at jet spun, it was here, down to 7%, 6%. When you look at vortex spun, as you increase the amount of cotton, it's down that wonderful 4%, 3% level, which is disastrous for any further processing. So there are other limitations in terms of what you can do with the system. In terms of machine components, people are playing around with settings, they're playing around with different components, and these are typical results in terms of changing the setting, the distance between the jet and the drafting rollers. And you can see if you go from 20 millimeters to 90 millimeters, you get a strength increase. Again, from 20 to 90, you get a strength increase. And this group and this group have slightly different jet configurations. So Murata, in conjunction with the industry, are fine-tuning this machine to make it better. And then, again, the same sort of results apply in terms of elongation. Now, don't get excited, because I know I said we've got elongation about 4%. This is 8%, but this is 50% polyester, 50% cotton. So that's the reason for this significantly higher extension. Centrifugal spinning. Really old idea. Anybody that did anything in worsted spinning or viscose rayon spinning will know about this system. It's an old idea. It's arousing a tremendous amount of interest at the moment. And the reason for that is the properties of the yarn should be identical, or almost identical, to ring spun yarns. The other thing is, the last one, which is automation, is an essential feature of this system. At the last ITMA, excuse me, at the last ITMA, there was a centrifugal spinning machine shown by the Russian machinery company, which I don't intend to try and pronounce. This was hidden behind a modification to a weaving machine. And I read all the reviews of ITMA, written in all the journals, and I don't think anybody else saw this machine. And it's probably the most exciting thing that was there. It was a single spindle operating, proving a principle. And the idea of centrifugal spinning, it is not roller spinning, it's a totally different system, is you draft, and the yarn is then assembled inside a rotating cylinder. So as the cylinder goes round, the yarn is simply wound there. It is a winding system, but it also inserts twist. So by rotating this bottom component, we insert twist into the yarn and we wind it on the package. It is exactly the same as ring spinning, except for ring spinning inside out. In ring spinning, we form the balloon on the outside and wind in. In this case, we form a balloon on the inside and wind out. But the structure and property should be the same. The concept of this is to have an automated machine where we literally spin the package of yarn here into a small cylinder, and then we back wind it onto another package, and then have automation. Now, this is a concept drawing, but the key thing is they're talking already centrifuge speeds of 35,000, so say ring spun yarn quality at least twice the speed. Package size about the same as a ring spun package. Now again, the neat thing is this doesn't work. If you go back to the old worsted ideas, the philosophy then was, let's make big packages. So you use huge centrifuges, you collected the yarn inside, and once you made that yarn, you took that out and did something else with it, or you back wound from there. Now we're saying the best way is to use really small ones, go faster, and then wind them. Now, in terms of what else is happening, if you just do a pattern search on centrifugal spinning, you can see where else things are going on. We come up with all of these different pattern drawings. In this case, it's the simple idea where we wind inside a rotating cylinder. This one, more adventurous, is a Schlafhorst. Schlafhorst are producing a pattern on a system where they say, look, we spin into one box, and when that one is full, we switch our thread line path into another box. This one drops out, we wind it. So you've got one filling, one emptying, one filling, one emptying. Alternative approaches by other companies, again, the simple one of winding the yarn inside the cylinder. In this case, they say, look, wind it in the cylinder normally, but then shift the rollers across and back wind out into a winder. So you fill it, move it across, wind it out. The high-speed winding obviously empties this package fairly quickly. Those sort of things have got to be resolved. I think, if the system's going to succeed, the automation is the thing that's going to determine whether it's working or not. The last I heard, I don't know whether it's confidential, but I'll share it with a few of you, is Schlafhorst are currently spinning at 60,000, right? So 60,000 ring spun yarn quality. Now, if that succeeds, it's going to be a major, major breakthrough in terms of spinning technology. 5 minutes? What time's lunch? Soon. Where's the technology got us? here. All of those developments have brought about this. If we look at the number of spindles installed in the US, and I've restricted here to ring spun and rotor spun, it's a disaster. It's way down. Rotor spun's fairly flat, ring spun's come climbing down. I read in an airplane that statistics are really boring unless you sort of enlighten them, and I agree. And things like saying over a 76% change in ring spindles is meaningless. But if you say to people, the US has lost 8.5 million ring spindles in the last 10 years, it has an impact. And that's exactly what's happened. 8.5 million spindles down in ring spinning, rotor spinning fairly flat, jet and vortex increased slightly. Now, and this is the sort of image that people get of the spinning industry in the US saying, it's dead. The figures prove it. But if you look at this diagram, but do it a different way, instead of saying simply take the numbers, take those numbers and divide them by the world. You come with a percentage. You say, if we look at what's happened in ring spinning, it's been disastrous, but we've dropped from about 12% to 6% of the world's number of ring spinning positions. In terms of rotor spinning, we've gone from 8 to about 15%. We're still a major player. So not all totally gloom and doom. Another aspect is the driving force behind that decline is here. If we look at ring spinning 1990 to 2000, 60% increase in speed. Rotor spinning, same time frame, 40% increase in speed. Jet spinning, 45% increase in speed. If we go from jet spinning to vortex spinning, we're talking probably 100, 200, 300% increase in speed. And the frightening thing is, my throwaway for the day, every successful spinning system doubles in speed in the first 8 years. Right? So if you go back through history, successful spinning systems have always gone twice as fast in the first 8 years of inception. Like jet spinning did. Now, if we're talking vortex spinning, we're saying 800 meters a minute in 8 years if it's successful. And that's frightening. That is really frightening in terms of spinning speeds. The impact of that is if we look at production of yarn in the US, it went up. And I remember writing a short article in 1994 saying, whoa, we're going to be up here somewhere. Because the trends show that. Unfortunately, it went down again. And the interesting thing is NAFTA came in about here. And there's been a decline. Yesterday, one of the speakers said one of the major problems throughout the world in spinning is overcapacity. That's exactly what happened here. People were spinning because the US could be shown to be the cheapest spinners in the world. Because the mills were automated, there were no problems. We could spin yarn as cheap as anybody else. Nobody would buy it, and therefore there's huge overcapacity. What's happened is there's been a slip and we've back the balance. The red line is supposed to represent the growth which we'd expect in terms of potential markets. I've got machine makers who are really excited about this. They say, look, if the trend continues as it has in the past, at some stage it's going to go up. And there is a real market for new machines in the US because we're under capacity at the moment in terms of spinning. I think this is the last slide. The questions, conclusions. Interest in ring spinning. Yes, because the quality is acceptable. One of the strange things about spinners is they are really conservative. They don't like to change. They say, look, that's the way I've done it, that's the way my father did it, and my grandfather did it like that, and therefore it must be right. Ring spinning does produce a yarn quality which every other system is judged, and therefore will continue to be there. It's good all round. It's not perfect in any respect, but it's good all over. In terms of compact spinning, major problem I see in compact spinning is it's expensive. It really is expensive. And if I look at most yarns, I'd say, what's the advantage? If I want to produce a really strong yarn, I'd say, forget staple spinning, use a filament. If I say, I've got a problem with hairness and pills, I'd say, Well, it's not usually cotton, it's going to be polyester or acrylic. And so for those systems, there may be some way of using this. But for most other systems, I don't know whether the advantages claimed for compact spinning will be realized. I know a lot of people in Europe have invested, but whether that's a good thing or a bad thing, I'd like to leave it open. That's why there's a question mark at the end. How fast can rotor go? I'm not bothered about rotor speed. I'm saying, look, let's cap rotor speed at 130,000. But if every rotor machine in the world was doing 130,000, I'd be happy. Does centrifugal spinning have a future? I have no idea. If I had a crystal ball, it would be wonderful. But I think if automation is right and the yarn quality is right, perhaps it will work. Final comment. I started off by saying, look, yarn quality is what we all talk about, but we don't understand. I did a survey about 5 or 6 years ago on something which seemed to be totally unrelated. That was looking at automation, application of computers, application of control systems to the spinning industry. And we did several questionnaires asking different questions. We put these all together and did the survey and assessed it. And when we asked where people would apply automation, where people would apply control systems and monitoring, 12 top answers were related to quality, but it was all process quality. Can I make my machine run faster? Can I have less downtime? Number 13 was the first aspect related to yarn quality. So whilst we talk about quality, in the real world, quality is way, way down there. As spinners, all we're interested in is producing as fast as possible, get it out the door and sell it. As weavers and knitters, other interests may be more important. And that's it.